Welcome to this tutorial. In this tutorial we're gonna see how to find the limit of a function, and we're gonna use some laws to do that. At the end of the class, everyone is expected to solve the limit of such kinds of functions. Let's get started. Let's consider a simple function f of x, simply a linear function x plus 1, this one graphically. So what happens to f of x if x is nearer and nearer to this value 2? So let's do some points on this by giving a table. For example, from this side, if you start from 3, when it is 3 it will be f of x, since f of x is x plus 1, so 3 plus 1 is 4, and when we nearer to 2.5 it will be 3.5, when it is 2.1, like this one. And if we approach nearer and nearer to, like for example 2.00001 from this side, this f of x will be nearer and nearer to 3. And also from this side, from this negative side, if we nearer and nearer to 2, let's start from 1 for example here. So 1 plus this 1 plus 1 is 2. So 1.5, it will be 1.5 plus 1 is 2.5, 1.9. So we are approaching to 2. Nearer and nearer. When we nearer and nearer to, f of x becomes 2 nearer and nearer to 3. So from both sides, from the left and from the right, as we x approaches to 2, this function's f of x is approached to this 3. So we say that the limit of f of x, x plus 1, the limit of x plus 1 as x approaches to 2 is 3. This is how we do the limit, but this is not the formal definition of limit. We're gonna see the formal definition of the limit, which is called epsilon delta definition, in next class. For today, if you know what is the value of f of x as x approaches to some value a, we're gonna say that the limit of f of x as x approaches to a is L, and we read this one as the limit of f of x as x approaches to a equals 2. Okay, what if, remember, note that even if f of x is not defined at a point 2, for example here, if it approaches to some number as x approaches to a, it have still a limit. The definition of limit is not a necessary condition to be defined at a. Let's do some examples for this one. For example, the past example is f of x equal to x plus 1. Let's multiply it both sides, I mean numerator and denominator, by x minus 1 over x minus 2 over x minus 2. It means x plus 1 times x minus 2 is x squared minus x minus 2 over x minus 2. So this function have the same limit, because except at 2 it is defined this f of x, since this will be cancelled out by this one, for x differ from 2, it gives the same result, x plus 1. So if we do the table, it has the same table, this value. If you substitute, check it, you may check it, it has the same value as the previous. So we say that still the limit of this function, the limit of this function is the same as the past one, which is 3. So f of x defined at a is not a necessary condition. The necessary condition for the limit to exist is it must approach to some number as x approaches to from both sides to the number a. So for this kinds of rational function, if we factorize this one and if there is a function that can be cancelled out, so we can cancel out this one and we can do the simplification. Okay, if you know this one, let's see some laws of limit. The limit of the sum or the difference of two functions is the same as finding the limit of f of x plus or minus the limit of g of x. So it is distributive over those functions, the limit. And also if it is multiplication, we can do separately the limit of f of x and the limit of g of x. We can do that. And if there is constant, we can factor out of the limit, and we can do the limit for this one, g of x. And if it is also a quotient, we can do separately f of x and g of x, and we can divide their limit values. The limit of any constant is itself, and the limit of any polynomial is the same as finding the value at a, and the limit of any rational function is the same except for this q of a is different from 0. It should be this one 0. If it is 0, we have to have a method to simplify this value, otherwise it is undefined. So using this limit laws, let's do some examples. Okay, the question is find the limit of these functions. Okay, the first functions is simply a polynomial functions, so we check by substituting these two, and so it is if it is polynomial, simply substitute it. So 3 times 2 square minus 5 times 2 plus 1 will be its answer. So this gives 3. So the limit is the same as the function at that value. For the second case, the limit is as x approaches to 1. If we substituted this one 1, so it will be undefined here, the denominator. If it is undefined, there must be a way to simplify, otherwise the limit does not exist. So can we factorize x minus 1 from this numerator? Yeah, because x squared minus 1 is the same as x minus 1 times x plus 1. So x minus 1 can be cancelled out by x minus 1 and it gives x plus 1. So finding the limit of this one is the same as cancelling this one and the limit as x plus 1. It gives, when we substitute 1 in place of x, we get 2. The third one is x squared plus 5x plus 4 over x plus 1 as x approaches to minus 1. So when we substitute minus 1, again the denominator is 0. So we have to have a way to simplify this one, if it is possible. Let's check it. X squared plus 5x plus 4. This is a quadratic function and it can be factored out x plus 1 times x plus 4, since the summation of their product 4 and their sum is 5, 1 and 4 can satisfy this one. So this can be factored out at this one, and x plus 1 will be cancelled with this one, and finding the limit of this function is the same as finding the limit of x plus 4 as x approaches to 1. So it gives something like that. The last example, the cube roots of x minus 4 over square root of x minus 8 as x approaches to 64. The first thing we need to do is checking the denominator. So if we substitute 64 radical 64 is 8, so 8 minus 8 is 0. So this is undefined since the denominator is 0. So we have to have a way. Okay, so let's first try by this one times cube roots of, rationalize the denominator, radical x plus 8, this one. So this one times this one will over this one, it is a minus b times a plus b, it will be a square minus b square. Radical x square is x, and 8 times 8 square is 64, so it will be like this. Now let's substitute and check. 64, still the denominator 0, so we must have a way to factor out something, and like this one. Anyways, let's check. So remember this identities. A square minus b square is a plus b times a minus b. Since we have cube roots here, we need to check if it is possible by factor outing x cubed minus x cubed is the same as a minus b times a square plus ab plus b square. So this can be expanded like this one, and then so x square 64 means it is 4 cubed, so 64, this 64 means 4 cubed, and this x means the same as cube roots of x the whole cubed. It has the same meaning. So this way we can expand these cube roots of x, that means x minus 64, this one x minus 64 can be the same as cube roots of x cubed minus 4 cubed. So this one will be like this. Thus x minus 64 is the same as multiplying these terms. Now let's substitute this value. Since there is a term cube roots of x minus 4 in the numerator, we can cancel out these terms. So here cube roots of minus 4, this will be the same as x minus 64 is the same as substituting this value, and we will cancel out this value, and we will get radical x plus 8 over cube roots of x square plus 4 radical of x plus 16, and substituting these values gives 16 over 16 plus 16 plus 16, which gives 1 over 3. This is how we find the limit. But for this kinds of limits, there is a powerful rule that we call it L'Hospital's rule. After we see the derivative, we will see back how to find the limits of this kinds of formulas. For now, you should know how to do the limits of these values by expanding simple identities. As an exercise, try this one, the limit of these functions, and we will do before the next lecture. For now, it's enough. Goodbye.